So in today's class, we're finishing up 7.4, which was about partial fractions. Remember, partial fractions are used anytime you have a rational function. It's a good idea to at least think about partial fractions. Isn't that right, Swashi? Yes. All right. So we were mid-problem last time in Wednesday's class, doing this one right here. I had gotten to the point where we had talked about what the partial fractions decomposition ought to be. We also integrated, right? We did a lot of our calculus and things like this. And I even brought up like a common misstep that I sometimes see students make, just getting kind of natural log happy. And then kind of talked about what the correct antiderivative of that is. And then so today I'd like to start kind of before class, I started jotting down this stuff here of just how to solve this system of equations. As you can see here, the system of equations really isn't all that bad, but still kind of this is a new topic. And so it kind of it's definitely worthwhile to go over all these steps one more time. So I set up, again, the function that I have. Remember, I'm trying to integrate this. I don't know what the integral is. It's quite a complicated thing. I'm trying to rewrite this into something where I do know what the integral is, right? Using this partial fractions decomposition. I've broken this down and I see that because in my denominator, I have this x minus 3 to a power of 2. Remember, the correct partial fractions decomposition, we need to have not only the x minus 3 raised to the power 2, but also to the power 1, right? These i's range all of the things less than or equal to the power of the factor here. In this case, x minus 3 has a power of 2. So now I'm going to go ahead and multiply through by this lowest common denominator, LCD. That's x minus 3 quantity squared. When I do that, on the left-hand side, things perfectly cancel out, right? The x minus 3 quantity squared on top cancels out with that on bottom, and I'm just left with x plus 1. Also for the term with the a in the numerator, right? These also perfectly cancel out, and I'm just left with a. However, when I distribute it to this term here with the b, only one of the x minus 3's cancel out, and the other one still makes it through. And so we have one more on top than we do on bottom, and that's why we get an x minus 3 there next to the b. Now we're going to go ahead and rearrange a little bit, right? And we're going to try to accumulate. Again, we're trying to make these the same functions, which means all of the coefficients have to be the same. So the stuff in front of the x's needs to be the same. So that is, right, we gather together all the stuff in front of the x's. In this case, only b is in front of an x. And so we know that b has to be 1. And then we gather up all of the constants. And so notice kind of I had to redistribute stuff, you know, as I moved from this line to this line. I gathered up all of the stuff with x's and all of the stuff with constants. And that's where this a minus 3b comes from. Now we can set these equal. We get b equals 1. Great time to use substitution. I just plug in 1 everywhere I see a b. That gives me a equals 4. And that yields my final result. See you, Swashi. All right. So I see there's at least one hand raised, and I did go through this fairly fast. So I'm sure there's a few questions out there. Let's hear what I should go over. So Kristen, you have your hand up. What's your question?
Oh, sorry. I think I left my hand up. Sorry.
Oh, okay. No problem. All right. Let's see. What would happen if you turned into the x minus 3 raised to the negative second power and tried to do integration by parts on this one? So could you do integration by parts? dvu. I suspect that this is one that you can probably do integration by parts on as well. It's not the thing that first comes to mind when I see a rational function, but sometimes problems out there, you do have multiple ways that you can integrate them. And so my guess anyway is that, yeah, integration by parts would work out. Why is the numerator for x minus 3 raised to the second power not ax plus b? Excellent question there. Just kind of to reiterate, because as we move to more complicated problems and whatnot, we will certainly need this as well. That this is the rule right here. When you have a linear term on the bottom raised to any power. So in particular, I have a linear term, x minus 3, and raised to any power, right? So it's being squared here, but also we saw it was the same for the first power. Notice that in this case, you only need an a on top. However, if you have an irreducible quadratic, that is a quadratic that does not factor, then that's when you need the ax plus b on top. And we'll see some situations where we need these coming up soon. Yuan, anything going on in the Q&A that we should talk about?
I think that's fine. One thing I want to clarify is the quiz 4 is probably not, some of them haven't finished the grading yet.
Oh, yes. Yeah, that's certainly true. Is that what we've told everyone, that we want to have quiz 4 done by Friday night. That's the deadline for the TAs.
Okay.
Okay, so let's go ahead and start on a new problem here. With this one, we can see that, again, kind of with the previous ones, that we need to factor the denominator. So in this case, right, the denominator is not factored. In the last one, it was nice, it was factored for us, but that's not always the case. And so we need to factor the denominator. And so I'm going to go ahead and maybe first rewrite this as x squared times x plus 1 dx. So now I factored out the denominator. In this case, I saw that, basically just taking out that GCF, the greatest common factor, there was an x squared in both terms. And so I was able to take that out. And now we have something that's nice and factored here. And so we could go ahead and do the calculus bit up front if we'd like. That is, I know that this is somehow going to be able to be transformed. And in fact, I think this is a good one to actually do wrong. Let's do this one wrong here. And then we'll make the mistake, just because I think that sometimes it's very useful to see this, just so that way, if you make a mistake on the quiz, you see kind of what happens, right? And you know kind of when to back up and try something else. So I'm going to intentionally here make this the integral of a over x squared plus b over x plus 1. I'm going to do it wrong, right? Of course, you can already probably tell, right, because we have this factor x being squared, we also need a term with x to the first power. But again, I kind of want to showcase what goes wrong in this case. So if I try to set this up and I do the algebra over here, you know what, let me keep going in red. Again, I'm going to have this x squared plus 5 divided by x squared times x plus 1. And I'm trying to make this equal to this here. My bad partial fractions decomposition. Again, I'm going to apply the exact same steps, right? I'm going to multiply through by this LCD, lowest common denominator, which we find over here. So this is going to be x squared and x plus 1. And so when I multiply through by that, we get x squared plus 5. For my term with the a's, the x squared perfectly cancels out, but the x plus 1 does not. And for my term with the b's, we get the x plus 1 cancels out, but the x squared does not. So now I'm going to go ahead and rewrite this, right? I'm going to do 1x squared plus 0x plus 5. Again, if we want these to be equal in terms of functions, and therefore would have the same antiderivative or the same integral, right? We need all of the coefficients to be the same. So that's why I notice I did like placeholders and stuff like this. And I wrote down the fact that the coefficient was 1 here. So now I'm going to align this maybe a little bit suggestively here. Bx squared plus ax plus a. So we can kind of see, again, we need the squareds coefficients to be the same. We need the linear coefficients to be the same, and we need the constant coefficients to be the same. Otherwise, they're not going to be the same function. And so what does this tell us? It says that b has to be equal to 1, right? The quadratic coefficients need to be the same. It tells us that 0 needs to be equal to a. The linear coefficients need to be the same. And it tells us that a needs to be equal to 5. The constant coefficients need to be the same. And notice what happens here. Exclamation point, frowny face, right? We're trying to set a equal to both 0 and 5. Therefore, 0 equals 5, and we've broken math and like right? Life is going sad. So yes, this is kind of what happens here when you don't choose the right partial fractions decomposition, is that you get some nonsense like this. When you go and you try to solve your system of equations, right, you get kind of this weirdness here. And so that's kind of what you need to be looking out for. If you make a mistake like this on the quiz or the exam or whatnot, this is the point where you say, oh, you know what? I forgot. I need this plus c over x, right? I need to have not only I equaling the power of the factor, x squared, but I need to have it less than or equal to the factor. I'm sure there's a few questions about this. So let's go ahead and pause really quick. Noah, you have your hand raised. Question.
Yeah, I just kind of missed out. Why is the c over x right there?
So the big thing here is that we need to have, when we're choosing the partial fractions decomposition, okay, right, how we're breaking this complicated fraction apart, notice that this bit right here, right, I takes on all of the values less than or equal to the power of the factor. So because we had x squared in the denominator here, we need to not only have x squared, but all values less than that as well. You know, you don't include 0 or negatives or anything like this. So we need to somehow include like a b over x. Now I had already used a and b, so it just made sense for me to include c over x, you know, thinking as if I was doing this problem on the quiz, I did it wrong initially, and then I had to go back and fix it. But if you were writing these things down, right, if you want to write it as a over x plus b over x squared plus c over x plus 1, that's also certainly fine.
Okay, thank you.
Yeah, definitely. Any other questions in the Q&A, Yuan, that we should talk about here?
Does the order of fractions matter?
No, you can add things in any order that you'd like. So you can rearrange these, and if you label your constants slightly different, that's fine. And, you know, maybe like we were just talking with Noah here, that, you know, if you make this a over x and b over x squared and c over x plus 1, that's also fine. We'll all get the same answer at the very end. Of course, there'll be a slight mismatch, you know, when we're actually solving stuff, but we'll all get the same answer at the end.
Another one is, were you able to solve a problem where the denominator is something like ax cubed plus b?
Ax cubed plus b? I mean, we can, right? The factoring on that, depending on what b is, probably doesn't turn out to be super nice. You'd have to do like the sum of cubes or something like that, and write b as the, you know, the cube of some cube root. So yes, it's certainly possible. I wanted to turn this blue because we're about to do it right now. All right, so let's see the right way to do it and kind of what we should get here. Kind of in line with what we've been doing for some of these other ones. I'm going to go ahead and do the calculus and integrate and everything here first. Then we'll do the algebra, and then we'll come back and throw things in. So if I was to integrate this, remember this x squared in the denominator here, that's the same thing as x to the negative second power. So when we integrate this, this becomes x to the negative first power, and then you multiply by the reciprocal of that new exponent, but the reciprocal of -1 is just -1, so you can write it like this. We get b and the natural log of the absolute value of x plus 1, and we have c and the natural log of the absolute value of x, plus a constant of integration, but I'm currently using c for something else. Let me go ahead and use k, I suppose, for a constant of integration. This sometimes gets used in Calc 3. So anyway, okay, so let's go ahead and do the algebra here, right? I've done all the calculus. Now I need to solve for what a, b, and c are going to be. Again, I'm trying to maximize my partial credit here, but still we have to do the algebra and try to figure out what these things are. So I'm going to set up very similar to last time, x squared plus 5 over x squared times x plus 1. But this time I'm using the correct partial fractions decomposition, which I'm setting up like this. But the strategy is going to be pretty darn similar here. I'm going to multiply through by the LCD, so x squared and x plus 1. When I do that, of course, on the left-hand side, things nicely cancel, and I'm just left with x squared plus 5. On the right-hand side, I get a x plus 1. I get b x squared. And I get c x times x plus 1. So notice again, there's a lot of canceling that happens. In particular, the one that we haven't talked about yet is this term with the c over x, in which case the 1x on bottom cancels with the 1x on top. Remember, I'm multiplying through all of my terms by this LCD, the x squared times x plus 1. One of the x's cancel, but one of them still remains. And of course, the x plus 1 doesn't have anything to cancel with for this c term here. Okay, so that's what the equation would look like without any fractions. Now let's go ahead and start grouping all of the like pieces. So again, on the left-hand side, I'm going to write this kind of suggestively, getting ready for what I know is coming up, where we set all of the coefficients equal to one another. And then on the right-hand side, we're going to try our best to group things. So I know, let's see, what we're going to have a bx squared here. Yeah, this is a little bit hard. Let me just maybe expand out with all of these parentheses first. Then I'll deal with kind of grouping. So if I distribute the a, I would get ax plus a. And if I distribute the cx, I would get cx squared plus cx times 1, which is just cx. Now I can go ahead and group things. So next to my x squared, it looks like I have a term with a b and a term with a c. So I'm going to go ahead and factor out the x squared from those, and that's what I would have. For my linear stuff, I would have an a and a c. And then for my constants, it looks like it's just a. So again, this is supposed to be equal to 1x squared plus 0x plus 5. So now we can go ahead and set up our system of equations. Again, the quadratics have to be the same. The linears have to be the same. And the constants have to be the same. So in this case, we're going to get 1 is equal to b plus c. We're going to have 0 is equal to a plus c. And we're going to have 5 is equal to a. Oh, that's very nice. We can go ahead and use their substitution method here, right? If a is equal to 5, plugging that in up here, we would get c has to be equal to -5. Otherwise, how are they going to add to be 0? And if c is equal to -5, I could plug that in up here and see that b has to be equal to 6, right? b plus c needs to be equal to 1. So, okay, b has to be equal to 6. So in this case, the substitution worked out quite well, right? We could do the substitution method once we had set everything up, and we get a equals 5, c equals -5, b equals 6. So now we're just going to go back in and plug these things. Let me write this maybe as nice as possible, right? So this would be -5 divided by x, right? You can see where the negative came from. And the a was 5. And the fact that we have x to the negative first power, that's the same thing as division by x to the first power. For b, we have 6, natural log of the absolute value of x plus 1. And for c, we have -5. So -5 natural log of x. Now, if you'd like to, you can change this to a plus c just for our constant integration, or you can leave it as k if you'd prefer, whatever you'd like. Now that, c is not being taken up by an actual number. I think a lot of the WebWork problems have c's as constants of integration. So I'll leave this as plus c. Okay. Any questions about this? Maybe let's first go to the Q&A. Any questions in the Q&A, Yuan?
Several questions comes from the a over x squared and the plus c over x.
Mhm.
Some of that is written as ax plus c over x squared. So yeah.
That's fine, right? So if you swap your a's and c's from what I did, right, you'll notice that when you solve, you end up solving a equals -5, right? So because I called it c, but you called it a, right? You get the same value, but we're just calling it different things, right? So you would get a equals -5. And likewise, you would get c equals 5, right? So if you swap them from what I called them, and there's not like a unique right way to do this, but if we swap what we're calling these things, then our intermediate steps look slightly different, but still we get all the same values. And when we plug them in, we get the exact same answer.
And I think they were saying is they're using ax as the numerator of x squared. They use the ax plus b, and then it's not a over x squared. And they
Oh, I see. So yeah, there. I guess if you do some random Google searching or you use another book or whatnot, I have seen it before that instead of using the method that we're talking about here, that you can do like ax plus b all divided by x squared, in which case this is the same thing as a divided by x and b divided by x squared, right? So this is maybe one of the first steps that you would do. And notice that we have the exact same terms. We have a constant over just x, and we have a constant over x squared. And so yes, that also works out. It's equivalent to what we're doing here. Is that more in line with what they were asking?
Yes.
Okay, cool. All right, let's do another one. Example number 9. Again, we're getting kind of more complicated here with each one of these. And I also want to kind of just point out between example 9 and example 10 here, they look quite similar. One has an x squared plus 9 in the bottom. This one has an x squared minus 9 in the bottom. Sometimes I see people, when they get a problem like this, they try to factor the numerator. Remember, that's not a part of this, right? You don't need to factor the numerator. I don't know if this factors or not, right? I haven't thought about it. I'm not going to think about it. All you have to do is factor the denominator, right? And so I'm going to go ahead and spend a little bit of time rewriting my denominator here, leaving the numerator just the same. Oops, that's supposed to be a 4. One of the worst 4s I've ever done there. So when I factor the denominator here, I'm going to get x minus 3. And we have a difference of squares here, right? So when I factor this, x squared minus 9, I get x minus 3 and x plus 3. And so now it looks like we have 2 of these x minus 3s. So maybe my final way that I'm going to write this before I actually go for partial fractions is going to be this x minus 3 quantity squared times x plus 3. Now with it written like this, I can confidently say what my partial fractions decomposition needs to be. So in this case, it's going to be the integral of a divided by, I'll do x minus 3, b divided by x minus 3 quantity squared. So notice we have all of the values of I that are less than or equal to our power of our factor. In this case, the power of x minus 3 is to the second power, right? And so we need also the first included in that for the correct decomposition. And then we're going to have c over, and since this is just x plus 3 to the first power, that's all you need. If you'd like to, right, we can do the calculus right now, which is kind of what we've been doing, thinking about maximizing our partial credit here. And so when I integrate this, I get a times the natural log of the absolute value of x minus 3 plus b. And when I integrate something raised to the negative second power, remember, we're going to raise our power by 1. And then we're going to multiply by the reciprocal of our new power. So the reciprocal of -1 is still just -1. So I'll just go ahead and multiply by that out here. And then we're going to get plus c times the natural log of the absolute value of x plus 3 plus some constant of integration, which I'm going to call k for the time being, since we're already using the name c for something else. So now if I know what a, b, and c are, I can plug those in and I will get the exact right answer. So it's algebra time. Let's move off to the side here and do a little bit of algebra solving a system of equations. Again, our entire goal here was trying to make the function that we were given, that looks quite complicated here, equal to something that we can actually integrate. And so in this case, we said that there should be a way to make this equal to some a divided by x minus 3 plus b divided by x minus 3 quantity squared plus c divided by x plus 3. And we want these to be the same function, so that way they have the same integral. So these steps, you kind of get maybe quite bored of them. They're the same every time, right? We're going to multiply through by the LCD. Looks like don't have quite enough room on the left-hand side here. Let me just try to squeeze it in over here. X minus 3 quantity squared and X plus 3. And so if I multiply by this across the board, of course, on the left-hand side, things nicely cancel out. And you can see here, right, I told you, you don't need to factor the numerator. You don't even need to spend any time trying to factor the numerator. It doesn't matter if it factors, because this is the form that we wanted in, right? We're about to set the quadratic piece equal to the quadratic piece on the other side, the linear piece equal to the linear piece, the constant piece equal to the constant piece. So this is the best way to have it. If you spend a lot of time thinking about does it factor, does it not factor, right? Who cares? It doesn't matter in this case. On the right-hand side, one of the x minus 3's cancel for our a term. So we're going to have x minus 3 still left over, one of them, and x plus 3. For our b term, both of the x minus 3's cancel. And so we just have an x plus 3 left. And for our c term, the x plus 3 cancels, but the x minus 3's don't. So we get something like this. Still, okay, we have to spend a little bit more time with our algebra here, rewriting this and then gathering up all of the quadratic pieces, the linear pieces, the constant pieces. So, okay, this would be a little bit boring here. With this, if I FOIL it all out, we're going to get x squared minus 9. Let's go ahead and distribute this, the b to each piece. And then for this piece here, I think I get x squared minus 6x plus 9 in this. Now let's go ahead and distribute one last time ax squared minus 9a plus bx plus 3b plus cx squared minus 6cx plus 9c. That's a horrible c. Oof, don't do that. And again, this is supposed to be equal to our right-hand side. And so for our final step, before we see truly what our system of equations are, we're going to gather together all of the similar pieces on the right-hand side. So everything with an x squared, I see an a and a c. So a plus c together make up our x squared coefficient. All of the stuff with the x's. So let's see, these ones right here. So I have, let's see, a b and a negative 6c. They together make up all of our stuff with our x's. And then finally, all of our constant things. So we have 9c plus 3b minus 9a. That's all of our constant pieces. This needs to be equal to our left-hand side. Oops. And so again, quadratics need to be equal to quadratics. Linear things need to be equal to linear things. We want these to be the same functions, right? And so all of these pieces need to be equal if they're the same functions. We want them, of course, to be the same function so that they have the same antiderivative. That's really our end goal here. So we have a plus c equals 7. We have b minus 6c is equal to negative 35. And we have 9c plus 3b minus 9a is equal to negative 24. You can see that sometimes, with these more complicated ones, that the system of equations is a little bit messy, right? You have to spend some time trying to figure this out. And so again, there's lots of different ways that folks like to solve systems of equations, and all of them will work here, right? So if you're someone who really loves determinants of matrices and Cramer's rule and all that sort of stuff, more power to you. You can use Cramer's rule. If you're someone who likes using linear combinations method and adding line by line and all that sort of stuff, use that. And if you're someone who likes the substitution method, that absolutely works as well. With this one, I don't really see anything, lining up perfectly, for a linear combinations method. And so I'm maybe most inclined just to go ahead and use substitution. So let's go ahead. If I use substitution in this, I'm going to rewrite this first one as a is equal to 7 minus c. For the second one here, I'm going to write b is equal to negative 35 plus 6c. Notice that I got all of these, right, subbing in my a's and my b's for some number of c's. So now I can go ahead and take both of those and plug them into my final one to hopefully solve for c. So the final one would go 9c plus 3 And instead of b, I'm going to write this stuff here, negative 35 plus 6c minus 9a. And instead of a, I'm going to write 7 minus c. This needs to be equal to negative 24. So now I have just one equation and one unknown, right? I just need to solve this for c. So, okay, we need to spend a little bit of time. 9c, you guys are lucky with the TI-30s, the calculators and whatnot. They'll help you out with this. 3 times negative 35 here, right? When I go ahead and distribute that, it's going to be like 105 plus 18c minus 63 plus 9c equals negative 24. So let's see. I have all of these being added together. So what? I should have 36c over here. And if I move over all of the other pieces, let's see, I'd have negative 24 plus 105 plus 63. So all of those constant terms over here. And let's see here, negative 24. So that's going to be 81. And I'm combining those right now in my head, or trying to. 81 plus 63. So what, 144? Everyone get C equals 4? Yuan, can you confirm my math is decent? C equals 4 look good to you?
Yeah.
Okay. Good. That is the hard part right there. Once you've solved for one of them, it's so easy to find the others, right? Because you have these wonderful equations that we used, right? Once we have C equals 4, it just all falls into place. A equals 3. B equals, let's see, negative 35 plus 24. That's got to be what, negative 11? Yeah, so really solving for one of them is the hard bit, and then the other ones just kind of fall pretty easily. So, okay, why don't we go ahead and now plug these in and get our final answer. Again, A was supposed to be equal to 3. B was equal to negative 11. Notice there's another negative right here. So I'm going to go ahead and, 2 negatives being multiplied together will give us a positive 11. And I'm going to write this as x minus 3 in the denominator here. And then our C value here we found to be 4. And again, you can leave this as plus K or plus C, whatever you'd like it to be. That right there is my final answer. Any questions on this one here? Bit of a long one, right? We'll go to Anito first. You've got your hand raised.
For the very first step, when you multiply it by the LCD, you have on the left side x minus 3 times x squared minus 9. And then when you multiply by the LCD, you have x minus 3 squared times x plus 3.
Okay. Well, I mean, we know that those are the same though, right?
Yeah, okay. Just yeah.
But that's a good point just so that everyone else can kind of follow along. Whether you set it equal to the first line or the, once we've actually done some work on it, I mean, it's equivalent because, I mean, those are equivalent functions.
Yeah.
But yeah, it'd be probably better for just as far as, minimizing the number of, emails and stuff like this I get as far as people seeing this posted online later and wondering, hey, how did these things cancel out? This is probably the better one to write down. I agree.
All right, for sure.
Cool. Thank you very much.
Yeah.
All right, so let's see. I think we have another raised hand here. Riley, you've got the next question.
Hi, can you hear me?
Yeah, sure can.
Okay, so the first line in the green section, or
Yes.
actually the second one when we're like multiplying out the denominators,
Yes.
I know that in like the A is A over x minus 3 and B over x minus 3 squared, like those kind of came from the same. But when we multiply it to like the C value, would you only do x minus 3 squared and not like cubed because there's 2 of them?
The big thing here is that the same LCD needs to be multiplied through by everything across the board. Otherwise, we'll get, the wrong answer. And so whatever you choose, right, in this case, the x minus 3 quantity squared and the x plus 3 raised to the first power, you need to multiply that by everything, including this c term here. And so that gives us only the x plus 3's cancel in this case. And that's kind of where the x minus 3 squared, right? None of those canceled out. So those need to be in our next line. Did I answer your question at all, or did I miss it? Sometimes I miss it.
You missed it just a little bit, but I think I have it now. I think I'm okay.
Okay, yeah, I was a little bit confused about, I don't see anything being cubed. And so that
Yeah,
kind of,
so when you, never mind. I think I'm okay now. I'm okay now.
okay.
I understand.
All right, if you have a question, you know, if later on you're looking back on this and something's still confusing, you know, throw it up on Piazza. I'd be happy to help, okay?
Yeah, of course. Thank you.
Yeah, no problem. Anything going on in the Q&A that we should talk about you on?
Could you have left x squared minus 9 as that and make it x plus b over x squared minus 9 at the beginning?
You know, it's kind of similar to what we talked about up here with the x squared. Well, no, wait, even that there would be issues with. Would that be a fine partial fractions decomposition? I guess the biggest thing that I'd be concerned with x squared minus 9 is that I don't know how to integrate. Let's suppose that we did all this and that was legitimate and everything, and you were tasked with then integrating this, right? You found the partial fractions decomposition, and let's suppose that even though you had ax plus b in the top, that maybe this ended up being, you know, a is 0 and b is 1. So you ended up getting this. How do you integrate this? Oh, right? The answer is another partial fractions decomposition. You would have to break it up yet again. And so that would be quite a shame, you know, to do a great partial fractions decomposition and yet having another one. So I'm not saying that maybe necessarily that there's any internal inconsistencies that, you know, you wouldn't be able to necessarily do that if you really wanted to. The problem is we just don't know how to integrate this thing. And so that would be my main concern. Let's see, Jared, you have your hand raised. What's going on?
So when you're like first like making the partial fraction, does it matter which constant you associate with which like denominator?
No, nope. You can do any of them anywhere, so long as you give them different names, you know. And if you don't like capital A, B, C, you know, you can do, I wouldn't do X, Y, Z just because X is already being used. I mean, don't double up on the names. I know maybe computer scientists or whatnot, folks who like, you know, subscripts. I mean, you could do A0, A1, A2, stuff like that. Or in some computer programming language or whatnot, A1 and A2, and, you know, so I mean, yeah, you can name them kind of whatever you would want. At the very end, we'll all get the same result.
Okay.
Good. So maybe I'd like to start this one, but notice that all of these that I've done so far, we haven't had to do long division of polynomials. And so I do want to give a little bit of airtime to that as well. It is possible. I mean, you do see some of those as far as on the WebWork homework that do have the polynomial long division. And so I want to make sure, you know, we talked about this in the pre-class notes. I want to give a little bit of airtime to that as well. So let's at least set this one up. Maybe we won't find the constants for this one, and I'll just fill it in kind of after class. And then I want to make sure that we talk about some of this polynomial long division. So, okay, let's set this up. Here we have one of these things that we've alluded to several times. I mean, they do exist and everything. This is an irreducible quadratic. If you try to factor this, similar to trying to factor x squared plus 1, you would end up in the complex numbers. And so this thing cannot be factored over the real numbers. And remember, you know, we are in the real numbers, right? We're just doing real valued calculus here. And so we need to talk about the correct partial fractions decomposition for this. And of course, it comes up in the pre-class videos and everything like that. We have maybe a over x minus 2 for the first bit, right? Because that's x minus 2 raised to the first power. And then whenever you have one of these irreducible quadratics, you need to have bx plus c, right? You need to have a linear, kind of 1 degree lower, right? So you can think about when you have linears in the denominator here, linear factors, regardless of what power they're being raised to, you have a constant. And when you have an irreducible quadratic in the bottom, like x squared plus 9, you need to have 1 degree lower. That would be a linear thing. So this is going to be bx plus c over x squared plus 9. So this right here would be the correct partial fractions decomposition. So of course, it's going to take you a little bit of time to solve for what a, b, and c are. But let's suppose that you go ahead and find these things, and now you're tasked with having to integrate this. Right? How do we go about integrating this? And so I just wanted to kind of reiterate one more time that it's quite often a good idea, once you have this, to split up this fraction here, kind of in the old way, you know, before we had partial fractions, decomposition, and all that sort of stuff. You could just break up the numerator. And so you can make this bx over x squared plus 9 and c divided by x squared plus 9. So this is a fine way to break up our fraction here. And now let's talk about maybe the integral of all of these things. And this will be where I leave it before we start talking about the long division of polynomials. So when I integrate the x minus 2 piece, I'm going to have the natural log of the absolute value of x minus 2. When I integrate this piece, can anyone tell me how can I go about integrating this piece here? What would be the correct technique? Yeah, and a couple of folks have brought it up in chat and everything. Excellent, great job. It's going to be a u sub. So if you choose u to be equal to x squared plus 9, notice that the du is going to be 2x dx. And so notice you have one of these x's hanging around in the numerator that is going to help us out here. So this is going to end up being what? You'll have this b over 2, because that's with this 2 out here, times the natural log of the absolute value of x squared plus 9. I am going fast through this, right? This is something I will write out a detailed solution for this, but maybe, you know, you can't exactly follow what I'm doing here. That's fine. You should take it slow and do it yourself. For the third bit, how would we go about integrating this? Notice that the u sub's not going to work for this one. U sub's not going to work because we don't have an x on top. How are we going to integrate this bit here? Well, we have a couple of different options, but yes, it's going to be a tangent inverse. Tangent inverse, and what I believe it's going to be like x over 3, and this is going to be c over 3 here. Again, don't take my word for it. You know, do this out slowly and surely, deal with that 9 appropriately and all that sort of stuff. But I think you get something like this, plus some constant of integration. So again, we have this one right here is going to be a u sub. I'll fill in the details for that. And this one right here, you should say that that looks a lot like an inverse tangent. Right? And so that's how you should be thinking about integrating this. All right, so still we have to find what are those correct constants and then fill in some more details about how do you actually get those correct integrals here. So that's what I'm going to be doing after class as far as, you know, before I post the filled in version. Okay, with that, again, I want to give some airtime to this final bit here. All right, we'll take one question. I see we have a raised hand. So one question here, and then, like I said, I do want to talk about this last problem a little bit. Michael, you got the
Professor
floor.
McCombs, how's it going?
All right, how about yourself?
Good, really good. So for example 10, I wanted to ask, where did the arctan come in at? Because like I'm having a hard time processing that one.
So yeah, the big thing here is from chapter 6, we learned that the integral of 1 divided by u squared plus 1 du was this arctangent stuff.
Oh.
So notice that this lines up pretty close, right? We have some constant divided by x squared plus 9. This is good for u squared plus 1, right? And so it's going to be something with an arctangent. but it's not going to be exactly arctangent, right? We have to do a little bit of work in this. Back in our chapter 6 days, we would have gone ahead and factored some stuff out and kind of rearranged and stuff like that. We could also do this problem now with trigonometric substitution if you'd prefer in 7.3. That will also work to solve this problem.
Huh. Okay, thank you.
Yeah, no problem. All right, with that, let's give some airtime to this final bit here, and that is doing long division of polynomials. And so the first thing that I wanted to emphasize here is that you need to do long division of polynomials anytime that your degree of the numerator is larger than the degree of the denominator here. So degree larger than or equal to the denominator, degree of denominator, which I'll just denote like that. Let me include in here degree of numerator. Degree of the numerator is greater than or equal to the degree of the denominator. Notice in all of the other problems that we brought up, here we had x squared, and in the denominator, this would be x cubed altogether. For the one before that, again, we have x squared in the numerator and x cubed in the denominator. One before that, I mean, you can take my word for it, right? All of them, the degree of the denominator was always larger than the degree of the numerator. This is the first one, right, where we don't have this to be true. And so I didn't maybe emphasize this so much earlier on, but it's an important fact. When you have it greater than or equal to the degree of the denominator, we have to do polynomial long division. And so that's what I'd like to set up here. So we're going to go ahead and take x cubed plus 4 and divide it by x squared plus 4. And I set this up just like we did long division of numbers a long time ago. I find that it's very useful when we actually go and evaluate this out to have some placeholders. So in particular, I'm going to go ahead and write this as plus 0x squared plus 0x plus 4. So I'm going to write it just like this, placeholders. That way I don't forget anything. And we're going to, ask the same questions and whatnot that we did when we did a long division of numbers. That is, we're going to look at these kind of leading pieces here. And we say, what do I multiply by x squared to get x cubed? And hopefully everyone agrees that the answer is x here. So now that we have that, we're going to go ahead and multiply by each piece. So this gives me the x cubed plus 4x. And I'm going to line this up kind of right underneath where we should. And again, just like we did long division of numbers, now we're going to subtract this away. And notice that this works out very nicely where we have the x cubed minus x cubed. That gives us 0. And we still have 0x squared. So that's going to be, okay, still 0. Now we're going to have what? Negative 4x and plus 4. That's going to drop down here. And so now we check, right? We look at the degree of this. It's a first degree. Is that larger than or equal to this here? That'll tell us if we need to continue or not. In this case, it's not. And so this is going to be our remainder. So now we know that we can rewrite this x cubed plus 4 divided by x squared plus 4 is equal to the quotient x, so that's the thing at the top, plus our remainder, and this still needs to be divided by this original polynomial here, x squared plus 4. And so if you want to integrate this left-hand side, that would be the same thing as integrating this right-hand side. And so now you can go ahead and break this up a little bit with the negative 4 and the plus 4. And again, I'll do all of these steps kind of, before I post the solutions online. But again, you can see that there's going to end up being a part where you have to do u substitution. So that's the negative 4x over x squared plus 4. And there's going to be a part where there's an inverse tangent. And thinking about, how could you make something like this reasonable for a quiz or an exam? Notice that I've given a hint up here that would help you finish off that other part rather fast. All right. Well, that's kind of what I wanted to make sure to cover for this problem right here. I hear a cat, it's stuck somewhere or something. It's growling. I'm the only one in the house, so I'm going to go check on it really quick and see what's going on. And I will be right back to answer questions.